full handouts later this morning. These are just temporary placeholders so that we can at least start the lecture going through. It's my great honor to introduce Professor Sangho Lee. Professor Lee is currently at the School of Civil Engineering, Environmental. Let me try this again. He's currently at the School of Civil and Environmental Engineering at Kookmin University in Korea. Gentleman got his Doctor of Philosophy in Chemical Technology at Seoul National University in Korea. He has extended list of publications, over 120 publications, including 35 registered patents. He also is an editor for the Journal of Industrial Engineering and Chemistry, and also an associate editor for the Water Science and Technology, and also an IWA member for the Membrane Specialist Group. He has extensive experience working in desalination systems.
This kind of relationship. So SEC is actually the ratio of the total energy consumption divided by the water, fresh water production. And previously, we know that this, in ideal case, the energy is same as the product of pressure and volume. And this volume is same as the volume that we use here. So again, SEC in ideal case is actually same as the pressure that we apply to the system. So probably in the end of my today's lecture, I'll probably talk about some of the idea of reducing energy consumption in desalination systems. But the starting point is, if you have higher pressure applied to the system, you have to use more energy, because that's the starting point of the energy calculation. Higher pressure results in higher specific energy consumption. So the first thing you wanted to consider is how we can reduce the applied pressure. Of course, in this case, this pressure in ideal case is same or very similar to the osmotic pressure. So if you have a certain seawater, you cannot do anything about the osmotic pressure of that kind of seawater. So this approach is highly limited. However, even in such cases, you always have to understand this kind of relationship. So if you spend 1 kilowatt hour per cubic meter, it corresponds to the pressure of 36 bar. So, and if you spend more the energy in such cases, it means that it corresponds to higher pressure. So, if you have the desalination process with the applied pressure of 72 bar, it means that such desalination system spend at least more than 2 kilowatt hour per cubic meter. So that's like this thermodynamic value, minimum value. So you always have to follow this baseline. So this is why I'm emphasizing this concept. And then, since we are living in a real world, not an ideal world, we have to consider the discrepancy between the ideality and reality, which is called the efficiency. So efficiency means that in real world, we always have to lose some energy during its operation or transfer. So there is always a loss of energy during its utilization. It means that the actual energy consumption is always larger than this ideal or thermodynamic energy consumption. So this efficiency is very important, and this efficiency part is something that the engineers can handle. So the engineers cannot alter the thermodynamic relationship, but engineers can change a little bit about this efficiency. The energy conversion efficiency is the ratio between the useful output of the energy conversion and the input. So if you apply energy you get energy out, but we'll have some loss of energy. So by having this ratio of this value and this value, that's energy efficiency. So once you know this energy efficiency value, and you have to multiply this, this part should go here so that we have to have more, that's just a typo, so sorry about that. Anyway, by considering this efficiency, in such cases, we can have more realistic specific energy consumption. So, in summary, when we wanted to consider the energy consumption in desalination, we first have to understand the thermodynamic limitation, and then we also have to understand the practical losses happening in the system. So how much energy that we are talking about in the real situation? So, and how much energy will be required in ideal case, and how much energy will be required in real cases? Of course, the actual energy consumption depends on the systems and site and conditions. So we cannot easily generalize the energy consumption. But in this slide, we can just have some concept of the differences between the ideal conditions and real conditions. So I'll explain that a little bit for making you have the better understanding. So according to the thermodynamics, which I already show you in my presentation, the minimal the thermodynamic energy for desalination when we have the 0% recovery is around 0.7 kilowatt hour per cubic meter. In this case, 0% recovery means that we just have very small amount of fresh water produced during this desalination. So 100 recovery means that if you have 1 cubic meter of the seawater, and if you produce 1 cubic meter of the fresh water, in such cases, we call that we have 100% recovery, which is not really possible. So, but you know, that's the ideal concept. And 0% recovery means that we use 1 cubic meter of the seawater and just 0 cubic meter of this fresh water. So again, this is not the real case. So we are always talking about the recovery larger than 0% and smaller than this 100%. But in ideal case, when we have the smallest energy consumption, that's the condition that is the condition where we have very, very low recovery. So that's the case that we can expect the smallest energy consumption. So that's why we consider this condition here in ideal case. And again, that value is the minimum value in this case, which is 0.7 kilowatt hour per cubic meter. And if you increase recovery, of course, the energy consumption will increase because of the two reasons. The first one is if you increase the recovery, in such cases, the seawater or the salt water will be concentrated so that osmotic pressure will increase together with this recovery. So since we have higher osmotic pressure, we have to apply higher pressure to overcome the osmotic pressure so that we will have to spend more the energy to carry out this desalination. Another case is if you have higher temperature, in such cases, according to the Van 't Hoff-ification, which has the temperature term in the right side, so this osmotic pressure will increase. But this effect is negligible because in many cases, we are in the seawater, we are talking about the temperature between 15 Celsius degree to 40 or 45 Celsius degree. So this is kind of a very narrow region, and in such cases, although this osmotic pressure is affected, in fact, the salt concentration effect is much more important. So in general, temperature effect is not seriously considered when we consider the osmotic pressure of the seawater. But anyway, in theory, if we have the high temperature seawater, we'll have higher osmotic pressure, so we will have higher minimum thermodynamic energy. So that's the relationship that I'm talking about here. If you increase the recovery, the minimum energy or thermodynamic energy will increase. And in fact, if we go to the 100% recovery, in such cases, the concentration will be infinite. So we'll have very, very high salt concentration in the pit side, so it cannot be achieved in real desalination system. Then we also have to understand this graph, which is a little bit tricky, so I'm not so sure if I can properly explain that or not. When you apply this, when you calculate this energy consumption using this equation, the idea is if we wanted to reduce the energy consumption, we have to operate the system close to the osmotic pressure. So if we apply the pressure much higher than this osmotic pressure, of course this energy consumption will increase and we'll have higher specific energy consumption. And in real reverse osmosis system, the ideal condition that we want is we wanted to have the same difference between the osmotic pressure and the applied pressure. In reality, it's not possible. The reason is, I don't know if you already learned about the basic configuration of the reverse osmosis membrane system. But the reverse osmosis membrane system is when we have the pit, which is the seawater, and in the meantime, when we let this feed solution passing through this membrane vessel, we'll have the pressure water, and finally we'll have this brine from this vessel. And what's happening here is, if you just have a graph of the salt concentration in the solution passing through this membrane module, initially we have this salt concentration, which is same as the pit concentration. But since we continuously take out fresh water from this water, so salt concentration will increase something like that with this direction. So this is the direction along with the direction of this membrane module, and this is the salt concentration. So initially we have this pit concentration, but when this water is getting out of this system, we'll have the concentration which is higher than this pit concentration. The problem is, if you wanted to get water here, it's not possible to apply different pressure in each membranes or in different positions. So instead of having different pressure, we just use high pressure pump to apply the same pressure. So for example, if we have the osmotic pressure of 30 bar, in such cases we apply 60 bar of the pressure from the pit, and in the end the final solution may have 55 bar of the osmotic pressure. So we have to make sure that this pressure is at least larger than the pressure, the osmotic pressure of the brine, which is the water coming out of this membrane system. So in ideal case, what we wanted to do is to apply the pressure with the same difference between the applied pressure and the osmotic pressure. But in reality, we apply much more pressure in the beginning, and we apply very small value of the pressure difference between the applied pressure and this final brine osmotic pressure. So this is so-called this irreversible energy loss. In the ideal case, if we can follow this thermodynamic minimum energy, we can just have this energy consumption like this case. However, since we apply the constant pressure from the inlet, near the inlet, we spend excess amount of energy, and in the outlet, we spend less energy. So we'll have this area, which is the energy loss happening in the real reverse osmosis process. So again, if we can reduce this part, we can increase the energy efficiency, and we can reduce the specific energy consumption. But in reality, it's really hard to handle this part. So this is one thing that we have to suffer when we consider the application of reverse osmosis. Again, this is the graph that I already explained on the whiteboard. So the real membrane system looks like this. So we have a vessel and containing several elements, and we supply the feed water, and we get the concentrate or brine. And in this case, the inlet concentration and outlet concentration, they are different, and so that we have different osmotic pressure inside this vessel, so that we have different pressure differences, which is actually called the NDP, net driving pressure, which is actually the proportional to the water that we can produce from this membrane system. But anyway, this value is not equal, so we have an ideal behavior, which is called the irreversible loss of energy happening in such type of the reverse osmosis system. And we have another loss that we have to take for this operation. So when we consider irreversible losses, we just assume that the final pressure, the applied pressure, is the same as the pressure of the concentrate. So at the end of this membrane module, we'll not get any water. So in this case, the water production rate or water flux will be very, very low. And in the inlet, we can have higher water production rate. In practice, we cannot waste this part, so we needed to have the additional pressure to get water even near the outlet. So in addition to this region, we also have another region, green area, which is also the energy consumption that we have to consider in real reverse osmosis system. So this is the actual operating pressure, which is around 10 to 20% of the brine osmotic pressure. So if we have the brine osmotic pressure of 55 bar, in such cases, we needed to have at least 5.5 bar or 6 bar of the actual operating pressure. So this is why we have to apply 60 bar instead of 55 bar in real cases, because we wanted to have water here. Again, this is the minimum energy that is given by the thermodynamics, and this is irreversible loss, and this green area is the practical loss, and the actual energy consumption in the system is actually this rectangular area, which has three parts: thermodynamic energy consumption, and irreversible energy consumption, the actual energy consumption. So this is how we can understand the energy, these consumptions in the simple reverse osmosis system. In addition to these three different types of this energy consumption, in practical cases, we'll have other types of this energy consumption. For example, if you use high pressure pump, you will supply the electricity, but this pump cannot fully utilize this electricity. In other words, this pump cannot have the 100% of the conversion ratio from electricity to mechanical energy. So during the energy conversion, again, there will be an issue of efficiency. So in such cases, we'll have additional losses added to these rectangular region. So even though we only have 0.7 kilowatt hour per cubic meter of the SEC in reverse osmosis system, in actual plant we are talking about 2 or 3 kilowatt hour per cubic meter of the energy consumption in real reverse osmosis process. So let's have some numbers. Assuming that we have 50% recovery, it means that we get 1 cubic meter of this seawater and we produce 0.5 cubic meter of the fresh water, and we get 0.5 cubic meter of the brine. So that's the meaning of 50% recovery. And in such cases, the theoretical minimum energy is 1.06 kilowatt hour per cubic meter, because it's larger than this 0.7, because we consider 50% of recovery. Our practical minimum energy when operated at the thermodynamic limit is 1.56 kilowatt hour per cubic meter, which consider these irreversible energy losses. But at least we need to have higher energy consumption than this value to have the actual operating conditions. So for best seawater reverse osmosis system consumes more than 2 kilowatt hours per cubic meter of the energy. And later we'll see that, but without having intake or pre-treatment or post-treatment, we cannot operate the seawater desalination system. So in addition to the reverse osmosis, we needed to have other processes that will spend more energy. So even if the reverse osmosis consumes 2 kilowatt hour per cubic meter of this energy, the actual plant will spend more than 3 to 4 kilowatt hour per cubic meter. So this is why we come up with the number of 3.5 or 4 kilowatt hour per cubic meter when we talk about the energy consumption of the seawater desalination plant. Of course, if we consider brackish water desalination, since we have lower osmotic pressure, we'll spend lower amount of this energy. But in case of this brackish water desalination, there is no standard number for the energy consumption, because brackish water has different characteristics and different salt concentrations, so there's no the standard value. But in case of the seawater, seawater has almost constant characteristics, so we can have this kind of a standard number. Again, depending on the region, seawater characteristics, or the type of process, we'll probably have different numbers for the specific energy consumption. This is another graph that make you have a better understanding of the situation. Again, in this case, we assume we have a slightly different condition. Instead of 3 grams per liter, we have 3.5 grams per liter of the salt concentration in the seawater. In such cases, we have slightly higher thermodynamic energy requirement even at 0% recovery. So in the previous case, we talk about 0.7 kilowatt hour per cubic meter, but in this case, we have higher salt concentration. So this minimum value is 0.79 kilowatt hour per cubic meter. And in many seawater desalination systems, they have the recovery of around 40%. So 40% is more like a standard value for the seawater desalination. And in this case, this value increases to 1.32 kilowatt hour per cubic meter. And for having enough water production rate or water flux, in this case, in addition to this pressure, in addition to this energy, we have to spend a little bit more energy, so this value will increase to 1.59. And by considering the other efficiency issues like the pump efficiency and membrane efficiency and other operational efficiencies, it can increase up to 2.0 kilowatt hour per cubic meter, which is probably one of the lowest energy consumption recorded in many in a report. And in real case, in real large-scale seawater desalination plant, we'll talk about the energy consumption around 2.5 to 3.5 kilowatt hour per cubic meter. A typical system, if the scale for the capacity for the desalination plant decrease, in such cases, the SEC value increase, because if you build the system smaller, in such cases, the efficiency will decrease again. So in such cases, if you decrease the system size, will have higher value of the specific energy consumption. So in very small seawater desalination system, you can even see the energy consumption of more than 10 kilowatt hour per cubic meter. So that's something you have to understand. So again, depending on the system configuration, feed characteristics, or other conditions, we'll have different numbers of this the energy consumption. And in addition to the energy consumption by this reverse osmosis, we'll have other parts that can also use energy. For example, pre-treatment, post-treatment, intake, and discharge, and even if you consider all these parts, but you will have other energy consumption caused by the problems associated with the membrane. So for example, if the membrane fouling occurs, membrane fouling means some impurities are deposited on the membrane surface, so the membrane performance will decrease, and in such cases, you have to increase higher pressure to get the same amount of water. So in such cases, the pressure increases, so the energy consumption increases, and that's another reason that you will have an increase in the energy consumption. So energy consumption is not only the problem of reverse osmosis, but also the problem of other parts. So if you wanted to reduce the energy consumption of a desalination plant, you have to have this larger picture, a big picture about this energy consumption. So this is one of the picture that actually show which part uses energy in the seawater desalination. So again, reverse osmosis, the part that uses the largest amount of energy. So this is just an example, but in this example, this reverse osmosis part spend more than 72% of the total energy consumption by the plant. However, the remaining 28% of the energy consumption is distributed to the other part. For example, intake can use up to 5% of the total energy consumption. Pre-treatment can use around 10%, and post-treatment can use product water delivery can use 8%, and other facilities can also have to use some energy. So if you add up all these energy consumption, you can eventually have the total energy use of 3.9 kilowatt hour per cubic meter in this example. And in fact, this number is a very small number, very low number. So if you can maintain your plant in such condition, it's very successful. So it's a very nice case, very good condition. Okay, we can start with the idea of changing the devices and changing the size of the system to reduce the energy consumption in seawater desalination. So in this slide, we see some of the graph showing the relationship between the plant capacity and the efficiency of the devices. So the first graph shows the pump efficiency as a function of the flow rate. Flow rate means the size of the pump. So the meaning of this graph is if you increase the size of a pump, the pump efficiency will increase from 0.4 to around 0.9 or more. So it means that even if you have the same type of pump, depending on the size of the pump efficiency will change significantly. So in this case, if you supply the electricity, less than 40% of the electricity can be converted to the mechanical energy. So the efficiency, that's why we have the efficiency of 0.4. But if you increase the pump size, in such cases, we'll have more conversion ratio, so the efficiency will increase. In other words, the specific energy consumption will decrease. And if you look at the pump, there are two parts. The first part is the pump head, which actually convert the mechanical energy from the motor to the mechanical energy or kinetic energy to the water flow during this pump. And that's the meaning of the pump efficiency. And the second part is this motor can get electricity and it can convert the electrical energy to the mechanical energy to run the pump. So that's the meaning of motor efficiency. And in case of the motor efficiency, it's not as sensitive as the pump efficiency to the size of the pump or size of the motor, but it still depends on the size of the device. So it means that if you increase the size of a pump, the efficiency will increase. By the way, if you wanted to have the whole efficiency from a high pressure pump, you have to multiply this pump efficiency and motor efficiency to get the total efficiency. And total efficiency depends on the flow rate or the size of the pump. So again, if you have a very small scale pump, the efficiency is less than of 0.4, and if you increase the pump size, in such cases, you'll have higher efficiency. And this is one of the reasons why we cannot decrease the specific energy consumption in a small-scale desalination system. Because small-scale desalination system where the water production is less than 100 cubic meter per day, in this case, the total efficiency is less than 0.5, which is a big handicap compared with the larger scale desalination plant, which has the total efficiency of more than 0.8 or 0.9. So due to this kind of relationship, if you calculate the specific energy consumption by considering these efficiencies, it is highly dependent on the plant capacity. So if you consider the plant producing only 110 cubic meter per day of the water, it has the specific energy consumption of 8 kilowatt hour per cubic meter, which is a significantly large number. But if you increase the plant capacity more than 10,000 cubic meter per day, in such cases, the specific energy consumption can be reduced lower than 3 kilowatt hour per cubic meter. Another thing that we have to look at is the variable frequency driver, VFD. VFD is the device to control the speed of motor so that the pump can have ability to change their production rate or change their pressure depending on the loading of the system. It is required in the case where the fluctuation in the salt concentration in the seawater happens, or fluctuation in the temperature of the seawater happens. And in this case, if we have the high temperature seawater or low temperature seawater, we have to adjust the power of the pump to optimize the energy consumption. And it can be done only with this VFD device. So by changing the frequency of the pump rotation, motor rotations, in this case, we can reduce or increase the pump power so that we can always guarantee the high efficiency of the pump. Otherwise, the pump efficiency will decrease, or we have to adjust the output of the pump by using valve or other devices. Again, in such cases, the pump efficiency will decrease significantly. So VFD is inevitable if, for example, in Korea, where we have seasonal variations in summer and winter, a country like Korea, VFD is not an option. It's just something that we must have, otherwise the specific energy consumption will be very high. In Middle East countries, traditionally, they didn't use VFD because this VFD is relatively expensive. So if you wanted to buy a large size VFD, its cost is substantial. But now, since the energy reduction is very important, the desalination plant built recently have this VFD device to adjust the pump speed and then increase the energy efficiency and then reduce the specific energy consumption. So by attaching VFD, we can improve the pump efficiency by 3 to 8%. Sorry about the Korean letters. I forget to change that. And another very important device is the energy recovery device, ERD. And I'll talk about that a little bit more with the following slides. And but reverse osmosis desalination system has had a very significant improvement and advances by inventing this kind of energy recovery device. And historically, people started to use a prototype energy recovery device, and now we have a very sophisticated and very high efficiency energy recovery devices that can guarantee the very high efficiency of the reverse osmosis system. So there are different kinds of the energy recovery device, which I will explain a little bit one by one. And depending on the type of the energy recovery device, the energy recovery efficiency changes. So for example, the Francis turbine, which is a very old energy recovery device, only has the recovery efficiency of 75 to 80%. On the other hand, the modern energy recovery device such as PX or Dewar has the energy recovery ratio efficiency of 98%. The meaning of this energy recovery ratio is, in fact, you have to understand why we needed to have an energy recovery device. In seawater desalination system, where we have the high pressure pump, again, if we can use VFD, we can improve this higher the pump efficiency, and if we increase the size of the pump, again, we can increase the efficiency. But in addition to this part, if you just look at the reverse osmosis system, what's happening is, so that's feed, that's brine, and that's product. And assuming that we have 40% of the recovery, means that we have feed of, let's see, 100 cubic meter per day, and brine is 60 cubic meter per day, and product is 40 cubic meter per day. So that's the 40% recovery that we are talking about here. Let's say that we apply 60 bar of the pressure to the inlet of the membrane module. In such cases, since this part the water passes through this membrane, so the water pressure will be 1 bar. But in this case, although we have a slight reduction in the pressure during the passage of the water through this membrane module, the pressure will be pretty much similar to this applied pressure in the brine side. So the pressure will be around 58 bar or something. So pressure drop through this module will be around 2 bar or something. And the energy, I told you that energy can be simply calculated by multiplying pressure and volume of water. And in this case, although it's given by a flow rate, but if you multiply the time of operation, it's actually the energy. So this part, PQT, is the energy that we apply in the inlet of the membrane module. And here, in the brine, if we just calculate this energy, it's still significant. So in this case, we apply around 600 of energy, but here we have 58 multiplied by 60, so it's around 3,000 and 6,000 and 3,600 of energy that's coming out together with the brine. It means that more than 50% of energy is not used during this reverse osmosis process, and this energy is wasted. And without recovering this energy, we cannot improve the energy efficiency. So energy recovery device, the role is to recover this energy and deliver that to the feed side of the membrane module so that we can collect this energy, and then the net energy consumption will be the difference between the applied energy subtracted by this energy recovered by this device. And energy recovery ratio, if it is 90%, 90% of this energy is recovered to the system. So this is why this energy recovery is a very nice idea to reduce the energy consumption. So this is the case, as I already explained, this is the case of the reverse osmosis system without having any energy recovery device. So this is the high pressure pump, and we increase the pressure of the feed, and a lot of energy is applied and introduced to this system. But a lot of energy is going to be wasted in this part because the energy in the brine cannot be used for producing any more water. So the high pumping cost will be expected, and we are going to waste a lot of energy, so we have to do something. So the initial idea was to attach this kind of turbine, and this turbine can use the brine flow, which has enough flow rate and enough pressure, and by contacting this brine with this turbine, we can get mechanical energy, and this energy can be delivered to the high pressure pump. So that can actually reduce the loading of the high pressure pump. This is a better idea than the previous case where there's no energy recovery. However, the problem is, as I already mentioned, that every time we convert the energy from one type to other type, we always have to experience some of the loss of energies. So in this case, the hydraulic energy in the brine is first converted to the mechanical energy by using this turbine, and this mechanical energy is again converted to the hydraulic energy to operate this membrane system. So we have two conversions, and of course, during this convergence, we'll lose a lot of energy. So this is why this Francis turbine or Pelton wheel type of the energy recovery device is not as efficient as the other types of the energy recovery device. So nowadays, nobody uses this type of this energy recovery device. And then people develop a better idea, better device, which is called a turbocharger. In fact, turbocharger is used in many the gasoline cars, and they utilize the same idea. So the role of turbocharger is to again, it delivers the hydraulic energy in the brine to the feed side. So in this case, there is no conversion from hydraulic energy to mechanical energy. So in this sense, the turbocharger is more efficient than the Pelton turbine or Francis turbine or Pelton wheel. So it's a better device than the previous energy recovery devices. So in this case, as you see that by passing through this turbocharger, initially we pressurize the water, and by passing through this turbocharger, it acts like a booster pump. Booster pump means if you have a pressure, but if it's not sufficient to operate the reverse osmosis, we have to increase the pressure to satisfy the final required pressure, and that kind of device is called the booster pump. And turbocharger is like a booster pump, but it does not use any electricity. Instead, it uses the energy in the brine of the membrane. And the final generation of this, the energy recovery device is the PX, pressure exchanger, or Dewar device. They share the same principle. Again, it works like a turbocharger, but it has special structures which can improve the energy transfer efficiency. So if you compare PX or Dewar with the turbocharger, the PX or Dewar have much more energy efficiency. So this is why many people nowadays use this type of the energy recovery device, and they can increase the energy efficiency and reduce the specific energy consumption. So the basic idea is inside this PX, there is a special rotating device which can directly deliver the pressure from the high pressure side to the low pressure side. So in this case, the brine has high pressure, but when it passes through the energy recovery device, the high pressure is delivered to the low pressure side, and when it gets out of this device, the pressure is released, and the pressure is transferred to the feed side. So this water has pressure to operate the reverse osmosis membrane. In fact, since the pressure is not as same as this one, so we may need to have a booster pump again, but the difference between the pressure here and pressure here is not significant. So we can significantly reduce the energy consumption by utilizing the hydraulic energy in the brine side. So in this case, energy conversion happens from hydraulic energy to another hydraulic energy. So we can expect high constant efficiency, flexible operation, and smaller pump for boosting the feed to the membrane system. So this graph shows how the efficiency of the energy recovery device changes with the flow rate. So the efficiency for PX or Dewar, this type of energy recovery devices are called isobaric energy recovery device, and they have very high efficiency regardless of the fact the flow rate to the energy recovery device. However, in case of Pelton turbine or turbochargers, it is sensitive to the flow rate. So in these kind of cases, if we have lower flow rate, the efficiency decreases significantly, so that we cannot rely this kind of device when we have the situation where the flow rate changes with the time. So the nice thing about this isobaric energy recovery system is that first, it has the constant efficiency, and it has the higher efficiency again. So by introducing this energy recovery device, the energy consumption by the reverse osmosis membrane reduced significantly, as you can just imagine from this example. And this is why reverse osmosis is widely accepted by industry, because before that, when energy recovery device was not introduced, reverse osmosis was not really attractive compared with the conventional thermal desalination systems, although the energy consumption was slightly lower, but still it uses a lot of energy, so that was not really attractive. But after using the energy recovery device, now reverse osmosis, the desalination outcompete with the thermal desalination. And then this is like the standard techniques to improve the energy efficiency and decrease the specific energy consumption. And beyond them, there are new approaches to further reduce the energy consumption. For example, the ISD, internally staged system. In this case, inside the membrane vessel, people put different types of the membranes by equalizing this product flow rate along with the membrane membrane vessel or membrane module. The reason is, in the previous lecture, I mentioned that if there's a significant difference between the water flow rate in the inlet and in the outlet, in such cases, irreversible energy loss happens, so that energy efficiency, the specific energy consumption increases. And so solution is, if we can have same flow rate throughout this membrane vessel, in such cases, we can reduce the irreversible the energy loss. And in fact, since the osmotic pressure are different along with this vessel, it's not really possible to have the same flux or same product flow rate or inside the vessel. But if you use the membrane with different permeabilities, even if they have different driving force and different osmotic pressures, we can significantly reduce the variations along with in the product flow rate along with this membrane vessel. I guess this concept is a little bit complicated, so I don't really know if you can fully understand what I'm talking about. So, in summary, this is a kind of variations of the conventional arrangement of the membrane element inside the vessel. And by using different types of the membranes, it is confirmed that it can reduce the energy consumption as well as improving this permeate water quality. And this is why this concept, the ISD, is accepted in many places in membrane desalination. So this is an example of comparing two different types of the arrangement of the membrane element. This is a conventional arrangement where people use same membrane element in a vessel. However, in this case, people use two different types of this element. First element has a low water permeability, and the other element have the higher water permeability, so that we can actually reduce the changes in the water flux in the inlet and in the outlet. The effect is the actual reduction in the water cost ranges from 3 to around 6%. So by simply changing the membrane arrangement without changing the other parts, we can also reduce the water cost, which depends on the energy consumption in this system. So the reduction is around 3 to 6%. So again, it is also effective to reduce energy consumption by this reverse osmosis membrane system. Another modern approach to reduce energy consumption is closed circuit desalination. This is also a very difficult concept, but if I just explain in an easier way, it shares the same idea that we wanted to reduce the irreversible energy loss in a system. So as I already mentioned that in the previous lecture, this is the theoretical energy consumption, and this part is irreversible, the energy loss. And since we apply the same pressure from the inlet, we have this part as a loss. And ideally, if we can have a constant difference between the theoretical pressure requirement and applied pressure requirement, we can take out this part. However, in the conventional reverse osmosis membrane system, it is not possible to take out this part because we always have to apply the same pressure from the inlet. However, in the idea of this closed circuit desalination, the applied pressure changes with the time. So this is not a continuous system. This is a batch system. So we just recirculate the water on, and we continuously getting the permeate from the system. So initially, the water salt concentration inside the system is 3.5 gram per liter, but with the time it changes to 4, 5, and 5.5. So eventually, until when the final target salt concentration is achieved, the system is stopped and we take out all the brine inside the membrane system. The nice thing is, during this operation, we can increase the applied pressure in a stepwise manner. So the pressure follows with the osmotic pressure requirement in the system. So we can simulate this kind of situation. So we can minimize the difference between the ideal theoretical pressure requirement and applied pressure requirement. So we can take out this part so that we can again reduce the specific energy consumption. Again, this is a very complicated system. So again, I don't really know if you can fully understand this idea, but the idea of CCD is very popular in these days. So this is why I want to introduce this concept, at least for you to have a very brief idea about this concept. Another similar idea is the two-stage reverse osmosis. Two-stage means we have the first pressure for the first stage and pressure for the second stage. So we can change the pressure during this operation of the system. It means that if we only have a single stage, we have to start with this pressure, and this part is the irreversible energy loss. However, if we have another stage, in such cases, we can start with a lower pressure, and then when we achieve a certain point, we can increase the pressure and apply that. So this part can be eliminated. So compared with the single stage reverse osmosis, the energy gain or recovered energy is this part. So second stage membrane system is always more efficient and uses less energy compared with the first stage, single stage reverse osmosis. Of course, if we can have the infinite number of stages, we can significantly, we can achieve the ideal energy consumption. So we can actually approach the theoretical minimum energy. But in practical sense, it is not possible to have infinite numbers of the changes. So this is just the ideal assumption. In fact, we just needed to compare for a single stage and two stages system, and by adding one more stage, we can reduce the energy by 20% or more. So again, this is another idea to reduce the energy consumption. So this is just a summary of the slide, and if we compare the closed circuit and two-stage or three-stage and single stage uses the highest amount of energy, but closed circuit or two or three stages, we can reduce the energy consumption. And the differences between the single stage and other variations of the system, the other variations increases with increasing the recovery. And the practical recovery in the seawater desalination is 40%. And under this situation, the SWRO, the specific energy consumption, is reduced by around 20%. So if you wanted to reduce the energy by 20%, it is one of the ideas is to apply CCD or two-stage reverse osmosis. Again, this is just early stage of this implementation of these new technologies. So still, this is the new trial, new attempts, and traditionally, many desalination plants still uses single-stage system. And another place, we may use the energy for getting higher quality of water from the seawater desalination is the second stage reverse osmosis when the boron is problematic. So if single stage reverse osmosis cannot properly handle this boron in the seawater, in such cases we have to use second pass reverse osmosis to completely reduce, to improve the rejection of the boron in the final product. However, again, as I already mentioned that by using the second pass reverse osmosis, we have to use more energy. So in order to reduce this energy consumption by this second stage system, there are a couple of different variations to remove boron without spending substantial amount of energy. So for example, by using ion exchange resin, which is specific to the boron removal, we can just remove boron without increasing the specific energy consumption. Of course, the problem is if you use ion exchange, you have to frequently regenerate this ion exchange resin. So instead of spending electricity or energy, you have to spend some chemical to regenerate the ion exchange resin. So people have developed the idea of combining ion exchange and second pass RO to both reduce the energy consumption and have the adjustable or manageable amount of this chemical consumption. And when we come back to the reverse osmosis system, in fact, reverse osmosis membrane system has three major parts. The first part is the membrane or membrane vessel, and the second part is pump or ELD, which are the equipment. And the third part is the pipes that connects the membrane to the pump or other equipment. So these three things are the main component in the reverse osmosis membrane system. And we studied the way of reducing the energy consumption in the membrane, in the vessel, and in the pump, and in the ELD. And the final part that we have to look at is the pipe. And when water passes through this pipe, there will be a friction loss, and it is expressed as the pressure drop. And in the reverse osmosis membrane system, pressure is the specific energy consumption. So if you have the pressure drop, in such cases, specific energy consumption will increase. So we have to minimize the pressure drop happening in the pipe network. So the meaning of pipe network optimization is we can wisely select the proper pipe so that we can minimize the friction loss caused by the water flow through this pipe. It's not simple because we cannot easily calculate how much friction loss will happen inside the pipe of the reverse osmosis membrane system. In fact, there are so many pipes in the membrane plant, desalination plant, so it's not possible to measure friction losses in every pipe. That's so time consuming and it's practically impossible. So instead, what we can do is to use computer software. The computer software, they can accurately calculate how much pressure drop will happen by selecting a certain size with a certain dimension. And by having that kind of this computer model, without even building the system, prior to that construction, we can even calculate how much pressure drop will happen within the system. So I'll show you the example of how we can do that. So this is an example for a small-scale desalination plant consisting of reverse osmosis membrane and high-pressure pump and feed pump or some other things. So this computer model simulates the actual reverse osmosis membrane plant with this PNID diagram. And by using these dimensions in the pipe, we can just calculate how much friction loss will happen throughout this whole system. So this is the computer model again. So this is the reverse osmosis membrane part, pre-treatment. And we have many different pipes. And in each case, we have the 5-dimension pipe connections and pipe materials and pump characteristics. And the computer software can calculate how much friction loss will happen and how much pressure is distributed within the system. So if you select one pipe in a system, we can actually know how much pressure in this pipe and how much flow rate in this pipe. And then again, we can just calculate this energy consumption. So this is just a case study, so you can just take a look at that. So this is the case with the 500 cubic meter per day of reverse osmosis membrane plant before the optimization. And before we actually adjust the pipe size or pipe materials and pipe connections, the total pressure loss through the whole system was 2.7 bar by the calculation. And we can convert this pressure to the actual energy loss, which is 3.921 kilowatt. And if we can convert that to the specific energy consumption, it corresponds to the specific energy consumption increase by 0.188 kilowatt hour per cubic meter. So in the pipe, we spend this amount of energy. So of course, it's not possible to completely eliminate this energy consumption because every pipe will have a certain degree of this friction. So this part cannot be completely eliminated, but by adjusting the size of the pipe or other part, we may be able to reduce that. So how much we can do that? And in this simulation, with the same plant, by changing the pipe size, pipe length, or pipe location, and by doing this kind of optimization, the result changed. So previously we had a total pressure loss of 2.7 bar, but in this case we can reduce to 1.63 bar, which corresponds to the 0.075 kilowatt hour per cubic meter. So we can significantly reduce the energy consumption by this. We can reduce 0.075 kilowatt hour per cubic meter of the energy consumption by optimizing these pipe properties in the system. So this kind of technique is very important and useful when you first plan or design the reverse osmosis desalination plant. So without having trial and error, we can start with the optimized pipe network, and then we can reduce the unnecessary energy loss caused by this pipe network. And even if you have the same system, by changing the operating conditions, the specific energy consumption may be changed. So in this case, there are two important operating parameters shown in this calculation. The first operating parameter is the applied pressure. So in order to operate the desalination plant, we have to apply the pressure, but you can adjust the pressure from let's say 50 bar to 70 bar, and in this case you see how much energy consumption will be obtained depending on this applied pressure. And as you probably easily imagine, by increasing this applied pressure, the specific energy consumption will increase because, first of all, high pressure will result in high flux, and this will also result in higher recovery, so that the osmotic pressure will increase, so that we needed to apply more pressure, and this is why we have the higher pressure, higher energy consumption with the high applied pressure. In case of this recovery, I'll show you the whole picture of how recovery affects the specific energy consumption. But in this case, by increasing the recovery, the specific energy consumption tends to decrease. And in fact, this is kind of complicated to understand because recovery can affect several different parts. Imagine a reverse osmosis system with this configuration. This is the typical configuration. And let's say that we have the recovery of 40%. And we want to produce 100 cubic meter per day of the permeate. In this case, if we can neglect the recovery of the pretreatment and other parts, we probably needed to have 100 divided by 0.4, which is 250 cubic meter per day of the water required as the feed water to the reverse osmosis. It means that we needed to have the intake with this capacity, pretreatment with this capacity, and so that we can have this amount of this feed solution to maintain this recovery. Let's consider the case that we have the recovery of 10% instead of 40%. If we reduce the recovery, in fact, the final salt concentration in the brine will decrease because due to the increase in the recovery, the final brine concentration will be affected. But by reducing the recovery, the final brine concentration will decrease. So in fact, the osmotic pressure in the system will decrease. However, the problem is, in this case, recovery is not anymore 0.4, so we need to have the intake of 10,000 cubic meter per day and 10,000 cubic meter per day for the pre-treatment. So we have to spend a lot of money for building and operating this intake and pre-treatment. And another problem is if we have 1,000 here, 90, and 100, it's not easy to recover the energy in the brine and to deliver to the feed site. So although it looks like it's better to reduce the recovery to reduce the energy consumption by reducing the osmotic pressure, in reality, it's not always true because this recovery affects not only the osmotic pressure but also the intake, permeate, and energy recovery device. So this is why we have this kind of complicated picture. So if we just consider reverse osmosis, even without considering pretreatment and intake, if we have the energy recovery device, that's the light green line. In this case, if we start with the recovery of 40%, and by increasing the recovery, we can actually, the energy consumption is actually increases. So the idea is around 40%, we have the minimum energy consumption for the reverse osmosis combined with the energy recovery. However, without using this energy recovery device, in this case, the energy consumption will have the minimum value around 65%. So the behavior of the reverse osmosis with and without and with energy recovery device changes. So this is why the effect of recovery on the energy consumption is far more complicated than you can simply expect. So in order to determine the optimum recovery to minimize the energy consumption, you probably need to run some computer simulation to find the optimum point. Otherwise, you will not be able to find the best, the desired recovery ratio to reduce the specific energy consumption. And another aspect that we have to consider is membrane fouling. So the membrane always tended to be fouled by collecting the impurities in the seawater. So this impurity may be particles or bacteria or inorganic salts or other things, but they can easily attach to the membrane surface, and if they form a layer on the membrane surface, it can actually disturb the water passage, so the membrane efficiency, membrane water permeability will decrease. So membrane fouling is not really a good thing, and in terms of the energy consumption, if the water permeability of the membrane decreases, it leads to the increase in the specific energy consumption. So this is the relative degree of membrane fouling, and if it increases, and this specific energy consumption can increase significantly. So if it is possible, we have to minimize and we have to manage the membrane fouling. And there are 3 different ways to handle this membrane fouling. The first one is to enforce the pretreatment. If the system uses a media filter as the pretreatment, we may consider the changes to the ultrafiltration or dissolved air flotation so that we can have higher quality treated water from the pretreatment, and then that can be very effective to reduce the fouling in the reverse osmosis membrane system. The second idea is to add chemicals such as sulfuric acid or antiscalant or coagulant. A coagulant is just for the pretreatment, but anyway, by using these chemicals, we can alter the solution chemistry in the seawater so that we can remove these potential pollutants, and then we can retard the membrane fouling. However, whatever you do that, eventually the membrane will be fouled, and then you have to recover the performance by applying physical cleaning or chemical cleaning. So if inorganic salt deposit on the membrane surface, we can use acid to dissolve this inorganic deposit. And if organic matters deposit on the membrane surface, we can use the base or other chemical to eliminate these organic layers. So by doing that, we can in theory, we can just handle this membrane fouling. In practice, it's not really easy to handle membrane fouling because, first of all, we cannot directly see through the membrane because it's inside the vessel, and the membrane is in the configuration of the spiral rounds. So before we cut out the membrane, it is not possible to see what's going to happen, what's happening. So diagnosis is very important, but we always have to decide something with very uncertain information, so that it's kind of very tricky part. But in the plant where there are a lot of experienced engineers, they know how to handle this membrane fouling. So this is the picture to show the surface of this reverse osmosis membrane. In fact, if you look at the reverse osmosis membrane, it just looks like a paper, and the top layer is shiny, and the other layer is matte-like texture. And this shiny layer contains the active layer made of the polyamide polymer, and the thickness is it's very thin layer, so several micrometer layer coated on the polysulfone film, and that's the reverse osmosis membrane. And the property of this layer is relatively hydrophobic. It means that it can capture the organic matters and other foulant, other chemicals in the seawater pH solution. Surface is rough, as you can see, so it can capture this kind of pollutant here. And so it's prone to fouling. So that's why we always have to experience membrane fouling when we use the reverse osmosis membranes. And again, this is vulnerable to the inorganic foulant as well as organic foulant and microorganisms. So it's also prone to biofouling. So after the operation, when you get the membrane from the membrane vessel, you'll see different aspects of this foulant inside the membrane module. For example, in the first case, what you see is the brown layers, which is probably organic matters or biofilm, or it may be like this iron oxide. But before we analyze that, we cannot identify what they are. And in this case, the fouling happens not only on the membrane surface, but also in the membrane channel. So the membrane channel is blocked, and it means that water cannot properly pass through these membrane modules, so that problem happens here. So when it happens, you can probably detect that without even taking out the membrane by monitoring the pressure drop from the inlet to the outlet of the membrane vessel. So if this clogging happens, in such cases the pressure drop will increase, and then you can easily imagine that this kind of things is happening. And this is so-called the spacer of the inside the membranes. And the spacer, the basic goal is to separate the membranes and guarantee the feed channel or permeate channel. But when fouling happens, this spacer can be blocked by this inorganic or organic foulant, so it cannot work anymore, so that again this will significantly reduce the efficiency of the original membrane. So anyway, membrane fouling is problematic, and it's not it's a problem not only in terms of this energy consumption, but also in terms of the membrane lifespan, lifetime, and membrane performance. But another thing that we also have to consider together with the membrane fouling is the maintenance issue. Because reverse osmosis membrane, as you saw in the previous slides, it is a very fragile, thin polymer film. So it's not something very, very strong. So if you use in the water for more than 3 years, the property of the polymer will change so that the membrane cannot retain its original performance. So what's happening here is if you operate the membrane and if you just monitor the applied pressure in the membrane system, and the applied pressure can be changed by the seawater temperature. So in this case, this is actually the simulation in Korean seawater. So higher pressure can be obtained in winter, lower pressure can be obtained in summer, winter, summer, winter, summer, winter, summer, something like that. And why we have the gradual increase in the applied pressure with the time. And in this case, the applied pressure has the same meaning with the specific energy consumption. And the reason is, with the time, the membrane performance changes. So membrane water permeability reduced by 7%. That's kind of the average number, but that actually depends on the specific size. But in average, we can say the average annual reduction is around annual reduction in the water permeability is 7%, and annual increase in the water salt permeability is 10%. It means that the membrane will lose its original performance. So after use of 3 or 4 years, we have to replace the membrane even without having any significant membrane fouling. And this number may increase if you use too much chemicals. So if you want, for example, if you wanted to control membrane fouling by applying frequent chemical cleaning, in such cases the chemical can affect this membrane, so it can accelerate the degradation in the water permeability and reduction in the salt rejection. So the membrane lifespan or lifetime should be considered together with the membrane fouling control. So too frequent cleaning is not recommended in terms of both chemical cost and membrane lifetime. So this technique have been developed by previous researchers and engineers, and by applying this kind of techniques, the reverse osmosis specific energy consumption has been reduced with the time. So this is one of the results that compares the average specific energy consumption in 1970s, 1980s, 1990s, 2000 years, and after that. And that's the specific energy consumption in SI unit. So if you look at this, in 1970s, the specific energy consumption by a reverse osmosis membrane system, even without considering the pre-treatment and intake and post-treatment, the value was even higher than 11.4 kilowatt hour per cubic meter. So it's several times higher values, that larger numbers than the number that we are talking about in these days. So in other words, the performance of the membrane and the design of the membrane, the equipment for the membrane desalination, they were not very good to have an affordable energy consumption. And it has been reduced by developing new membranes, by applying energy recovery device, and by optimizing a new technique for the energy reduction. So people think that this energy consumption will decrease with the time. But another aspect that people think is there will be no significant energy reduction in the future. It's not the case that we can reduce more than 30% of the energy between 1970s and 1980s, because the energy that we are talking about in these days is actually very similar to the thermodynamic energy consumption. And we cannot actually reduce the energy consumption lower than the thermodynamic energy consumption. And we have a very small margin between the thermodynamic value, theoretical value, and the actual value that we can witness in the modern membrane desalination plant. So we'll have a marginal reduction in the energy consumption in the future, but not the significant one. So this is why we have to reduce the energy consumption from many parts and to collect this the total energy to have the substantial total energy reduction. And I already mentioned that if we can if we can increase the size of the plant, we can reduce the energy consumption. And this is true when the plant size is less than 20 or 30,000 cubic meters per day. But if the plant size is more than 50,000 cubic meters per day, in such cases, it is reported that this unit water cost is almost constant. In fact, there is a slight decrease with the increase in the plant size, but it's not really significant. So this is another characteristic, that the proper membrane desalination plant size ranges from 40 to 80 or 100,000 cubic meters per day. Okay, and that's actually the first part of the lecture today, and we can move on to the energy efficiencies and water cost in many desalination plants all over the world. And we'll also see some of the case studies for small-scale desalination systems, so that we can just have a better idea of how much energy is being used by many different desalination plants, and how we can understand this result. So first of all, I'll briefly mention about the water cost and energy consumption in the seawater desalination. Although we are talking about this energy consumption, but the reason why we have to look at this energy consumption is because it is related to the water cost. So we first have to break down this desalination cost, and then we'll see the contribution to the energy cost, and then we'll see the idea of how we can reduce not only this water cost, construction cost, but also this operational cost. So this is the general aspect of this general configuration of the seawater desalination, as you know. Intake, pre-treatment, reverse osmosis, post-treatment, and water distribution. And if you look at that, there are two types of these cost factors. The first one is construction, and the second part is operation. And of course, if there is a financing plan, there may be the cost related to the interest or other parts. But in this case, we just consider some engineering consideration, engineering part. So if we purely consider the engineering aspect, we only divide the cost into two parts, the construction cost and operating cost, including the energy cost, chemical cost, waste disposal, and labor and maintenance. And in this maintenance, we also have to consider the membrane replacement cost. So there are a lot of different reports regarding the cost breakdown in seawater desalination. So although you have the different numbers, you may have to understand that because depending on the study, they have different result and different statistics. But anyway, their range of these relative contributions of a specific part are similar, although they are not exactly the same. So by looking through this cost breakdown result, you may have some concept about how much the cost factors. So when we consider the construction cost, we can break down that into several parts. And if you imagine a seawater desalination plant, the first thing you may see is the equipment such as pump and ELD or other mechanical devices. So equipment and materials takes the most important part in the construction cost, which is responsible for about 30%. And civil engineering, although it's not really significant, but depending on the site, the civil engineering, the contribution may be larger or smaller. And this part is also site-specific. As I already mentioned that, depending on the situation and site, we may have to spend more money for the intake or less money for the intake. And membrane process, although people just imagine the membrane when we first imagine the reverse osmosis desalination, membrane cost in the construction is only about 10 to 15%. So the actual the part by the membrane is not really significant when we consider the desalination plant. Instead, we have to consider the equipment and other parts. Design cost, installation and services, and other parts, they just account for 25% of the total construction cost. And in this case, we have the cost breakdown for the operation, And if you look at the operation, around 50% is taken by this energy cost. So as you can imagine, this desalination plant uses a lot of energy. So during the operation, the energy cost is substantial. And membrane replacement, it actually depends on the size of the plant and the operation plan of the plant. But in general, this membrane replacement cost is less than 5%. So again, even if this is the membrane plant, the membrane contribution to the total cost is not really significant, not only in the construction, but also in the operation. Labor around 30%, chemical around 15%, and parts, we frequently have to replace valves or other things, and that's about 7%. And when we consider the energy, this energy can be explained by the energy consumption by the reverse osmosis and pre-treatment intake and water supply. And if you have the second pass systems, the second pass RO can use some amount of energy. So in fact, this ratio is similar to the ratio that you saw in the picture of the SEC values in each unit process in the desalination. So this is another interesting result. So if you wanted to reduce the cost for the desalination, what part we have to consider preferentially? So the answer is, if this part accounts for the substantial amount of this construction cost or operation cost, in this case, by reducing this the cost by 10% or even 5%, it can significantly affect the total cost reduction. So for example, as you already saw that this operation cost for the reverse osmosis is the most important part. And by reducing this cost for auto operation by 10%, we can approximately reduce total cost by around 1.9%. So this is one of the reasons, one of the places that you first have to look at to reduce the total plant cost. Labor cost and chemical cost and equipment cost, they are all also significant, but not as important as the auto operation cost. And this is why we spend some time here to talk about the energy reduction and energy consumption, because that's the part that we have chances to reduce the cost for seawater desalination. And this is another statistics to compare seawater desalination with other types of the desalination. Just like the case with the energy consumption, if you build the small size desalination plant, the unit cost will be significantly increased. And if you increase the size of the plant, the unit cost means the cost to produce the certain amount of this water. Since small scale plant will use a lot of energy, and the building and operation will be more expensive. So by reducing this plant size, the unit cost will increase. So in case of the seawater desalination, if the plant size is less than 100 cubic meter per day, the unit cost will be around 1.2 to 15 euro per cubic meter per day. This is just some value given by this reference. But what you can imagine is, in the small scale system, the cost range is very huge depending on the system configuration and system operation. So it's not really surprising to have such a very high number. Brackish water desalination, again, if we have a very small scale system, the unit water cost will increase. And by increasing the plant size, the water cost is very small. The MSF and MED, again, by reducing the size, we can have this high water cost. And MED in this case, it's not really possible to have a small-scale MED system. So we only have one value, and we don't have any data for the small-scale MED plant. Anyway, if you just compare seawater desalination with MSF or MED or this vapor compression, reverse osmosis is always the cheapest option. However, if you compare this with the brackish auto reverse osmosis, of course it's more expensive because we have to handle with the feed water with high salt concentration. For your information, this is another case study that shows the actual money spent to build 40,000 cubic meter per day of the desalination plant. The total installation cost, according to this report, was $30,000 million. The capital cost was 61%, and since this was the real project, so project engineering, project development, and financing, they account for around 39%. So capital cost, if you look at that again, the reverse osmosis system was the most expensive, and in this reverse osmosis system, not only the membrane but also pump and other equipment are included, and except for that, they are a little bit negligible. The operation and maintenance cost, if you look at in the previous case, the energy cost was around 49%, and in this case, the energy cost was around 55%, and chemical 6%, and in this case, the membrane replacement cost was a little bit higher than the previous example, but still, compared with the energy cost, they are all very, very negligible. Fixed charges, 23%, including labor, other maintenance, and other things. So by having all these numbers and assuming that this plant is going to be operated for the next 20 or 30 years, the water cost that include the capital cost and operational cost was 0.73 per dollar per cubic meter. And in this case, in this analysis, the energy cost was 30%. So it means that if the energy cost increases by 10%, for example, the electricity cost, sometimes it changes depending on the energy status. And assuming that it changes by 10%, in this case, the total water cost will change by 3%. So again, energy is very important part, and that's why we have to look at that. Again, we have another similar graph showing how much energy was used in the previous desalination project and how much energy is being used in the past 20 years of the seawater reverse osmosis system. So this energy consumption decreases significantly in the past 30 or 40 years. But in these days, this energy consumption is reduction in the energy consumption is a little bit marginal. So it's hard to believe that there is a huge reduction in the energy consumption in the future. And this is another data that collect the total water cost and the actual energy consumption in the desalination plant all over the world. So this in the left figure, we compare the water cost, and the plant built in 1990s was a little bit expensive, and the plant built after 2005 was the water cost around 0.5 US dollar per cubic meter. So this is a very small number here. And together with this water cost, this energy consumption decreased significantly. Although I don't know why they have these numbers here, but if you just look at the reverse osmosis, the energy consumption decreases with time, as we just saw that in the previous slide. Of course, there are some variations from this main trend, but the general trend shows that this energy consumption decreases by applying various techniques. So what makes this kind of changes? So in the 70s, people first developed commercial grade reverse osmosis membrane. So Sri Rajan, they first developed this thin film, this cellulose acetate reverse osmosis membrane in 1960s and 1970s. And that was the beginning of the reverse osmosis. And at that time, the energy consumption was very high. And first generation energy recovery device was introduced, which also has the reverse pump. And by introducing this technology, the energy consumption was reduced by 3.8 kilowatt hour per cubic meter. And then between 1980s and 1990s, the pump efficiency increases. So previously, the pump efficiency was less than 70%, but the pump efficiency increases more than 80%. So that actually changed it a lot to have a lower energy consumption. And together with that, this energy recovery device based on the Pelton turbines was introduced at that time. So another 3 kilowatt hour per cubic meter was saved by introducing these new technologies. And between this time, there was a significant development in the reverse osmosis membrane development. So low energy reverse osmosis membrane was introduced in the market, and the salt rejection was improved. So people did not need to consider multi-pass reverse osmosis membrane. So that's another reason to have an additional called the energy reduction. And between this time, highly efficient energy recovery device was introduced to the market. So pressure exchanger or DeWeer, they were introduced at that time, and that also reduced the energy consumption significantly. Now, the value will be a little bit similar to this one because there was no new technologies between 2006 to the present time. Instead of having a big technology, now we have the small technologies that can save the energy a little bit. And by collecting that and by integrating the effect of this energy reduction, we now have a desalination plant with small energy consumption. Okay, here we'll compare different desalination plants all over the world. So before we do that, we have to look at the places where the desalination plant were installed. So between 2010 and 2016, depending on the region, we have the total installed desalination capacity from around 80 million cubic meter per day to more than 120 million cubic meter per day. And there are places where there is a significant increase in the capacity, and the desalination plant in the Middle East countries gradually increase, and it also increased in other places. So that resulted in the significant increase in the total installed desalination capacity. So we have several typical desalination plants with the capacity and with some information. For example, in the first table, we have a list of the biggest desalination plant all over the world. The SA means the Saudi Arabia, and UAE means the Arab Emirate. And here, Ras Al Khaimah in Saudi Arabia has the desalination capacity of 1 million cubic meter per day. And in other places, they have huge sized desalination plant built and operated recently. And that actually includes the desalination plant based on the thermal desalination principles. And if we narrow down to the reverse osmosis desalination plant, the biggest one in the record is the desalination plant in Israel. Shorek has the capacity of 510 cubic meter per day, and the Algeria, Australia, and United States, they all also have the very big size reverse osmosis desalination plant. And these are the list of typical large-scale desalination plants in United States. And in the United States, especially in the region of California, they suffer from a serious drought in these days, in recent years. And they are seriously considering the introduction to the seawater desalination. Of course, there are many people who are against the construction of seawater desalination in the United States, especially considering the impact to the marine environment by the discharge of this concentrated out of brine. But anyway, it's on and off, but it's not very fast. But in the United States, in the West states, they tend to accept the seawater desalination with the time. So they'll have more desalination plant in the future. In Asian region, it is reported that China is going to build a very big seawater desalination plant in the future. And in the other countries, they are also considering the construction of the large-scale desalination plant, the capacity more than 400,000 cubic meter per day. And in Australia, around 5 to 10 years ago, there was a serious drought also in Australia, and that initiated the construction and operation of the seawater desalination plant. And so, as a result of that drought, they built several desalination plants in Melbourne, Perth, and Sydney, and some of them are operational, some of them are not. But again, Australia suffer from this water shortage on and off. So they also needed to build more desalination plant in the future. Spain is another country in Europe building and operating large-scale desalination plant. So its size is smaller than the other desalination plant in Saudi Arabia or or Australia, but their size is still very large. It's several times larger than the desalination plant in Korea, so it's a very large plant in many places all around this Spain and other European countries. In fact, in Europe, Especially there are many small or medium-sized desalination plants in European countries, so their numbers are very large. And in this table, I only list the large-scale desalination plant, but in addition to them, there are other small-scale desalination plants in European countries. Saudi Arabia, and they are planning to have a larger desalination plant in Jubail, and their size will be more than 1.5 million cubic meter per day. And in fact, Saudi Arabia is one of the leading country constructing the seawater desalination. So their project will go on in this country. In North African countries like Libya and Algeria, they also have this seawater desalination plant. So these are some of these well-known desalination plants, and I want to look at some of the details about these some desalination plant in some countries. So for example, this is well-known desalination plant, the Ashkelon seawater reverse osmosis constructed in Israel. Their capacity is around 320 cubic meters per day. That was commissioned in 2005, and their recovery is 40%, and their salt concentration is 40 milligram per liter, and the energy consumption is slightly less than 4 kilowatt hour per cubic meter. So it's very energy efficient. And the secret of this plant is, first of all, they adopt this dual isobaric energy recovery device. So it has the energy recovery efficiency more than 90%. So it can significantly reduce the energy consumption. And the second secret is they introduced the concept of the pump station, which is shown in this picture. And the pump station means instead of the individual pump in each train of the reverse osmosis system, they share a pump, bigger pump for several trains. The advantage of having pump station is, as you've already seen in the previous slides, if you increase the pump size or plant size, we can increase the pump efficiency so that we can reduce the specific energy consumption. And in this case, although they did not change the plant size, by changing the pump size, they can have the benefit of same benefit. So this is why they use the pump station. So anyway, by having this efficient system, their energy consumption was not high, and so their water cost was, I don't know, this is the initially reported number, and this water cost may change with the time, but initially they reported the water cost of 0.53 US dollar per cubic meter of pressure water production. This is another well-known seawater desalination plant located in Singapore. This is Tuas seawater desalination plant. Its size is smaller than the Ashkelon desalination plant. Its plant capacity is 136,000 cubic meters per day. And their feed solution, salt concentration was lower. So instead of having the salt concentration of over 40,000 milligram per liter, they only have 35. So they can have the benefit of lower osmotic pressure. And the operating pressure was lower than the previous case due to the lower osmotic pressure. So, but energy consumption was slightly higher than the previous case, and this is probably because of the size of the pump and other aspects which were not properly optimized, although they share the same energy recovery device. But anyway, their energy consumption was slightly larger, but due to the well-planned financing and other engineering aspect, they reported to have a lower water cost. So it's almost similar, but they also claim that this water cost of 0.47 US dollar per cubic meter of this fresh water. Another example here is the Fujairah desalination plant in this United Arab Emirates, and its size is you have to add this and this one, so I guess it's more than 450,000 cubic meters per day. One of the aspects that they have is they have the power plant, and they have two different units for the seawater desalination. So one unit is reverse osmosis, and the other unit is thermal desalination. And since they have steam near around the desalination plant, so they can have the benefit of using this steam from the power plant, so they can run this thermal desalination plant economically. And in addition to this thermal desalination, they combine this reverse osmosis desalination. So this is so-called the hybrid desalination, by having two different types of the desalination in the same place. So the thermal desalination, the capacity is 248 cubic meters per day, and with the operating temperature of 109 Celsius degree. Electrical energy consumption was 4.3 kilowatt hour per cubic meter. And there is no information for the thermal energy consumption, but considering the steam flow and steam pressure, we can probably calculate how much thermal energy is required to operate that. But I didn't calculate that because I was not really interested in the thermal energy consumption in this case. On the other hand, the reverse osmosis part has the capacity of 170,000 cubic meters per day, and which has the energy consumption of 4.8 kilowatt hour per cubic meter. So again, this is a reasonable value, and by combining that, they can have some operation flexibility as well as the synergetic effect. Another example that I want to share here is the desalination plant in Perth, Australia. And I heard that this Perth is a town where many the wealthy people lives around that. So this is a very nice place. And so they built a very nice reverse osmosis desalination plant. By the way, this is the place where this plant is located in Australia. And it has the capacity of 140,000 cubic meters per day. And the water cost is just like that. So in this case, reverse osmosis process uses around 68% of the energy, and intake, pre-filtration, and primary permeate distribution, their energy consumption was not really significant. Their cost was not really significant. And this reverse osmosis power consumption was approximately 20% of the total seawater reverse osmosis cost. And in this case, it is reported that this specific energy consumption was 3.44 kilowatt hour per cubic meter. So again, compared with the previous two cases, you can imagine that this plant is more energy efficient. And this is another example. Actually, it's in Korea. So this is a Gyeongsang desalination plant. The operation range is the recovery is slightly larger than this desalination plant in Middle East region. So this has a recovery of around 48%, and the feed pressure ranges from 51 to 54.5. Again, since the Korean seawater has the salt concentration of around 30 to 32 thousand milligram per liter, so considering that this salinity, we can operate this system with this moderate pressure conditions. And that's other conditions for the flow rate, and the temperature ranges between 17 to 24. But in winter, in fact, in this region, the seawater temperature is around 10 Celsius degrees. So low temperature operation strategy is required for this case. So in this, I think you've already visited this place, so you know how it is configured. So I don't want to explain the details. And in this case, when we monitor this plant, what you can see is the pressure and the energy consumption by the whole plant and by the unit process. And this is one of the examples of the operational record. And if you look at that, you see how much pressure is used, how much pressure is wasted, and how much pressure is required to operate this pre-treatment and reverse osmosis system. So in this case, we require the pressure of 57 bar for the operation of reverse osmosis, and the reason is at that time this was recorded in December, so the seawater temperature was very low, so that more pressure was required to have enough flow rate. So the pressure was slightly higher in this case. Oops. I think I missed one slide here, so that actually summarized the energy consumption in each unit process, but unfortunately we missed that, so I cannot explain that. But that's not really important, so we can skip that part to talk about other things. So in the previous cases, you see how much energy is used in a plant. But if you wanted to go into details about the operation and design of the plant, what we wanted to know is how much energy is supplied to the plant and how much energy is going to a specific place. So as we saw in the breakdown of the cost and energy consumptions, we want to see that the energy breakdown in a plant. Unfortunately, in many cases, it's not possible because they don't have enough equipment or enough tool to analyze the energy flow. So in this case, I want to show you some of the interesting and simple technique to show how much energy, the track of this energy inside the seawater desalination plant. And in this case, starting with some of the record and the data in a plant, we can actually convert that, and we can actually build some breakdown table, and we can just visualize this result. So first, we can start with the actual plant data, and then we can calculate the specific energy consumption for each unit process. And by adding all this energy by the unit process, we can actually have this total energy supplied in the plant and total energy wasted inside the plant and total energy going out of the plant. And then we can just use a chart called this Sankey chart so that we can just see the flow of the energy in the desalination plant. And this is an example of that kind of energy flow mapping. And by looking at this graph, you see the energy flows from inlet to the outlet. So total energy supplied here is, in this example, 3.3 kilowatt hour per cubic meter. And some of the energy was used to overcome the osmotic pressure. Some of the energy was used to separate water from salt. But some of the energy was wasted due to this irreversible energy loss, due to some friction losses, due to the losses by fouling or other problems. So if you supply this amount of energy, in the end you will have the energy used for working and energy wasted by this loss, and that ratio is actually the plant energy efficiency. And not only the reverse osmosis, but also the pre-treatment, intake, other post-treatment, they have the energy. But even if you supply the energy to the pre-treatment, this energy, some of the energy goes to the working part, and some of the energy is going to this waste part. So we can have this kind of energy flows, and in the end, we can collect these two types of the energies. So this kind of this energy flow diagram is very instructive. By looking at this, you can track down the status of this certain unit operation. So for example, if you feel that too much energy is wasted from the pre-treatment, you have to do something with this pre-treatment. And or if you look at other part and if it does not look very normal, in such cases, you can immediately find out the reason why it happens. And another techniques that we can use as a useful tool is to convert and compare energy consumption in different seawater desalination plant. In fact, I've shown you some of the examples, the Ashkelon, Tuas, and Perth, for example. Let's compare the energy consumption to see which desalination plant is the most efficient. If you just look at specific energy consumption, it seems that this Perth, which has the energy consumption, smallest specific energy consumption, seems to be the efficient one. However, in reality, it may not, because the seawater in Australia, seawater in Singapore, and seawater in Israel, they have different properties, different temperatures, different salinity, and the plant size are different. As I mentioned that, the plant efficiency is sensitive to the plant size, so it's not a fair comparison by simply comparing the specific energy consumption. At least we have to consider the effect of plant size, effect of temperature, and effect of this pH salinity. This slide shows the salinity distribution in the sea on the Earth. So, for example, in blue regions, the salinity was low, including Korea, and in the red region, like Europe and Middle East countries, they have higher salinity. And in Australia, they have intermediate salinity, and in Singapore, for example, they have low salinity. So since their conditions are quite different, it's not really meaningful to compare these specific energy consumption. So how we can convert and how we can have this fair comparison. So in this case, we actually develop a simple Excel sheet to convert the energy consumption from one plant to the other plant. So for example, if you have the data of this seawater desalination plant with a capacity of 100,000 cubic meter per day, and in this case, if you have this specific energy consumption of 3.3 kilowatt hour per cubic meter, the same process can only have the specific energy consumption of 4.3 kilowatt hour per cubic meter if the plant size is reduced to 2,000 cubic meter per day. So that can be theoretically calculated by considering the efficiency of the pump as a function of the pump size. Similar calculation, if you have the pilot plant in Korea with this capacity of 1,000 cubic meter per day, and if this energy consumption was 4.2, same process will result in higher energy consumption in Middle East countries. So that kind of things can be theoretically converted. So by doing that, by considering these kind of differences, you can have the fair comparison. The reason that I'm explaining here is sometimes people just compare specific energy consumption to compare the desalination plant. But I want to emphasize that not only the specific energy consumption, but also the plant size and salinity and temperature and other types of this. Sometimes recovery and other part should be also considered. So by considering all these kind of these conditions, we can probably compare the plant performance and plant energy efficiency. Okay, in this case, we have another result in the plant and this energy analysis in Galila plant. So I'm going to show you what is this plant and how we analyze this energy consumption and how much energy is being used by this plant. So this is located in United Arab Emirates, Ras Al Khaimah region. And in this region, the feed salinity was 42,000 milligram per liter, and seawater temperature, the real temperature is 35 Celsius degree, and the design temperature was 28 Celsius degree. And the plant size is not really large. It has the size of 68,000 cubic meter per day. But surprisingly, they claimed that their specific energy consumption was 2.84 kilowatt hour per cubic meter. So according to this data, it seems that this is one of the most energy efficient seawater desalination plant all over the world. So this is the reason why we wanted to look at this plant more closely to find out the secret of this low energy consumption. And some of these engineers in Korea visited this plant and analyzed this operation status and design parameters. In fact, this plant has this kind of configuration. So seawater intake is the starting point, and for handling the algae bloom, they have dissolved air flotation and some type of this filter and ultrafiltration and the single phase reverse osmosis membrane system. Since they have some allowance in the salt concentration in the product water, they didn't need to use second phase reverse osmosis. So they only have single phase reverse osmosis. And yearly they used pressure exchanger and high pressure pump. They use this type of high pressure pump, and they have conventional brine discharge. So if you just look at this flow diagram or flow configuration, it is difficult to find the secret of low energy consumption in this plant. So other operating and design factors were considered and investigated. So in fact, after the analysis, it was found that they have this intake pipe and 6 screens and dissolved air flotation with the chemical addition and ultrafiltration membranes, flux of 75 aromates with these conditions, which are not really special. The only thing that can see here is they have the inlet pressure of 3 bar and differential pressure of 0.3, and 3 bar is slightly a larger value. Reverse osmosis, the conventional recovery of 40% was adopted, and the membrane was not really special, and they used VFD, but they didn't use any pump station, and no ISD was adopted. So again, if you look at that, it's not a real special design or special configuration. Just one thing that's unique in this plant is there is no storage tank between ultrafiltration and reverse osmosis. In many cases, in general, people tend to use storage tank between pretreatment and reverse osmosis for operation flexibility, but in this case, they eliminated this tank so that they can reduce the energy loss by having this pump, by having this tank. But anyway, that's the mass balance. So they have around 700 and 800 cubic meter per hour of the water intake, and that was delivered to the reverse osmosis system, and the final water production was 22,700 cubic meter per hour. And initially they started the pressure of 0.53 bar, and final pressure is 1.4 bar, and the operating pressure is 58.6 bar. So that's all the information that we had, and we know that this total energy consumption is 2.94 kilowatt hour per cubic meter. So with this information, we started to have the energy breakdown by having some modeling and by having some in-depth analysis. So first, we analyzed the reverse osmosis based on the membranes used in this plant and based on the design conditions that was used, and the pressure drops measured in each place was considered in this simulation. And according to this calculation, the pump efficiency was determined to the 86%. And by using this value, we could calculate how much energy was used by this reverse osmosis system. And once we determine the energy consumption in a reverse osmosis system, we can also determine the energy consumption by other parts. And surprisingly, compared with other desalination plant, in the Galila plant, the contribution of energy consumption by this seawater reverse osmosis is very large. So it accounts for more than 80% of the total energy consumption in a plant. So it means that they did not successfully reduce the energy consumption for the reverse osmosis, but they could be able to reduce the energy consumption by other parts. So total energy consumption is very low according to this kind of calculation and according to the data from this plant. So this example also shows how we can analyze the energy flows and energy consumptions in a real plant. And then it also shows some of the idea of how we can reduce the energy consumption in a plant. Instead of reducing the energy consumption in a reverse osmosis system, they could be able to manage the energy consumption by other parts. So in the end, they did a very good job, and they had a very low energy consumption. Another thing that was not included in this slide is their final TDS of the product water was around 500 milligram per liter. So in Korea, many people don't like to drink the water with such high TDS. However, here it is allowed, so they did not need to have the second pass reverse osmosis. So in this case, if we introduce the second pass reverse osmosis, we have to spend more than 0.2 or 0.3 kilowatt hour per kilometer. So if you add this value and this value, the total SEC might be 3.2 or 3.3 with the second pass reverse osmosis. However, since they didn't need to have that, so again, they could be able to reduce the energy consumption by more than 10%. I guess this may be the last part that I will explain today, so I can have some time to explain this part. So here we've seen many cases. So the energy consumption in a large scale plant, energy consumption in a small scale plant, and we see some of the rough data as well as in-depth analysis. In this example, what I want to show you is to have a better understanding of the energy consumption as a function of this operational parameter. And again, I want to show you how we can optimize energy consumption in connection with the other operation targets. For example, we want to reduce the energy consumption, but we don't want to have low photon rejection in the plant. So there may be a condition that we can reduce the energy consumption and reduce the photon concentration in the final water at the same time. So that kind of things can be done by introducing some theoretical models. So since this is the last part, so I want to talk about some more theories about this prediction of the reverse osmosis membrane plant, which allows the prediction of this specific energy consumption. So that's another thing that I want to explain here. So in this example, our target is a small scale second stage. Sorry, not the second stage. Second pass, two-pass reverse osmosis desalination plant. So in this case, again, we have the intake and pre-treatment consisting of the membrane system. And first, reverse osmosis, which is the seawater reverse osmosis. And this energy recovery device, such as pressure exchanger, is attached. And second pass reverse osmosis, the water reverse osmosis membrane was attached at the end of this system. So in this case, the total energy consumption is the sum of the energy for intake plus some energy for pre-treatment and energy for first reverse osmosis and energy for the second reverse osmosis. So you see how each unit process energy consumption changes with the changes of the operating conditions. So in order to have this kind of calculation, we needed to have a theoretical model and some computer softwares to estimate how much flux, how much pressure, how much energy consumption will be given. And here I don't want to explain details about the theoretical model, but I want to show you some of the meaning of these equations because that may be instructive and useful for qualitative understanding of this desalination. First of all, when we introduce the theoretical model, since this is the membrane system that separates water from salt, there should be at least two parts. The first equation for water transfer and the second equation for salt transfer. So this is the equation for water transfer, and this equation, although it looks very complicated, it's a very simple equation. The meaning of this equation is you will have higher product water flow rate or flux if you have higher net pressure. So in this case, net pressure is the difference between the applied pressure and the pressure loss terms. And this pressure loss term include osmotic pressure and other pressure drops in the vessel or other pressure losses in a system. So, for example, if you have the osmotic pressure of 20 bar and if you apply the pressure of 40 bar, and if there's no other losses, in such cases, the net pressure is 20 bar and the flux is, in this case, let's say the flux is 10 LMH. And if you apply 50 bar instead of this 40 bar, in such cases, net pressure will increase to 30 instead of 20. In such cases, the flux will increase 15. Flux will be 15 instead of 10. So that kind of simple relationship is reflected in the first equation. And the second equation is also same, but we have some part that consider the effect of temperature. But if you just don't consider this part, this equation is also very simple. This equation means that this salt transfer through the membrane is not affected by this water flow. So this salt transport is controlled by this salt concentration difference. So it's hard to explain without drawing something. Oh, I didn't want to explain too much about that, but since I started, I want to talk about that a little bit, which is related to the principle of the desalination, reverse osmosis membrane. So let's say JW is the water flux or water flow rate through the membrane or flux, and JS is the salt flux or salt flow rate through the membrane. In this case, JW is proportional to the pressure difference and JS proportional to the concentration difference. So in this case, if we have more concentration in the feed and less concentration in the permeate, we'll have more salt concentration. But in this case, if we have more pressure in the feed and less pressure in the permeate, we'll have more water flux. So these two equations have such kind of meanings. So although it looks complicated, it's nothing. And other part, we can have equation for calculating osmotic pressure, calculating the pressure drop in an element or in a vessel. And this the pressure loss is expressed as the sum of osmotic pressure and other pressure losses. And other equation, I don't want to explain that, except for the final one, final two equation. This equation is actually the definition of recovery, which is the ratio of permeate flow rate divided to the feed flow rate, and that's actually the definition of recovery. And the specific energy consumption can be calculated using this equation when we use the energy recovery device. If we don't have energy recovery device, this specific energy is simply this term without that. So this is simply PF divided by pump efficiency, which I already explained that in the beginning of my lecture. But since we have to consider the energy recovered from the brine, so this term is introduced to this equation, and that's how we can calculate this energy consumption in a system with the energy recovery device. So I don't want to explain the details about this theoretical model. Instead, I'll just show you some of the results. But before I do that, I want to show you the actual plant that we carry out some experiments. And this is the plant with the plant capacity of 250 cubic meters per day. And the left part, this is the reverse osmosis membrane. In fact, it's not quite sure, quite clear, but it actually has two types of the membrane. So seawater reverse osmosis membrane and brackish water reverse osmosis membrane. And that's a tank that stores the water from the pre-treatment to supply the water to this reverse osmosis membrane system. And that's the high pressure pump. And I cannot see the energy recovery device in the picture because it may be located just here. And this is the pre-treatment ultrafiltration membrane and the hollow fiber types membranes, and they can filter out the colloid and other debris from the seawater. Okay, we have a better picture here. So this is a closed loop for the ultrafiltration membrane modules. And this is, I guess, this is the seawater desalination membrane, and this membrane is the brackish water desalination membrane. And this is the energy recovery device. That's the pressure exchanger, and this is the booster pump. I briefly explained that, but since the pressure from the PX is not sufficiently high to push the feed water to the membrane modules, so we needed to have a small booster pump to increase the pressure a little bit. And that's the high pressure pump. In fact, the plant size in this case was only like 250 cubic meters per day. But here, so the pump was not really big. But in a large scale desalination plant, the pump size is several times bigger than a car or a truck. So you can imagine a very large size pump. I guess you already saw that in the field in Busan or Gwangyang, so I don't need to explain this small size plant in detail. And before we apply this theoretical model, we first have to measure the actual data from the plant, which is shown just here. Since we have two stages, two passes, in fact, in the reverse, for the reverse osmosis, we have two graphs at the same time. So that's the graph for the first stage reverse osmosis, and this is the graph for the second stage reverse osmosis. The red line is flux, and the green, this blue line is the applied pressure, and green line is the temperature. So in fact, when we operate the desalination plant, we don't want it to adjust the water production rate. So if this plant capacity is 250 cubic meters per day, we always have to maintain the same flow rate. In other words, we always have to maintain the same flux because the membrane area is fixed. So by maintaining the same flux, we can always get the same water production. But if the seawater temperature changes, it actually affects the membrane performance. So if the seawater temperature is higher, the membrane water permeability is higher. So in order to produce the same amount of water, we don't need to apply high pressure. So if the temperature is high, we can reduce the applied pressure. And at the same time, we will have lower energy consumption. So this is why we have this kind of patterns. So seawater temperature increases from 10 to 26 or 27, 10 in the March, and 28 in the August. I guess it's around this time. And with that, you see that this applied pressure is reduced from 50 Celsius degree to this is an error or data hunting. It is reduced to around 40 bar. So you see that 10 bar was reduced by the changes in the temperature of 18 Celsius degree. So that's the general patterns that we can expect in the normal operation of this reverse osmosis desalination. And in the second pass, it was not really clear because after passing this first stage, the temperature fluctuation was diminished a little bit. So the temperature was similar. So, but we still have a lower pressure in summer and higher pressure in winter to maintain the same flux, and by adjusting the applied pressure here. So again, by looking at these two pictures, although it's not shown in these graphs, you can imagine that this specific energy consumption changes together with this applied pressure and water temperatures. In fact, this graph shows the changes in TDS and other factors, and depending on these water temperatures, the TDS also changes so that the water conditions changes with time. So that's the data that we could calibrate our theoretical model, and by having some trial and error model fittings, we could determine the following model parameters. I don't want to go over details about the model parameters because that's not something you want to hear that. Just one thing I want to mention here is in the first stage, reverse osmosis, we had this membrane element that has we have just one of this membrane vessel having 7 membrane elements with a membrane area of 37 square meter. And for the second reverse osmosis, we had 2-stage systems. So 2 vessels with, and each vessel has 3 elements, and 1 vessel with the 3 elements. So that's 2-to-1 configuration. So if I draw that, the actual configuration was like that. So that's the first reverse osmosis, which has 7 elements. And after passing that, we put 3 elements, total 6 elements, into 2 vessels and 3 elements in the last vessel. And the reason why we have this kind of configuration is because once the water passes through the first vessel, the flow rate will decrease. So to compensate this effect, we can just combine concentrate from 2 vessels into 1 vessel. So in this case, we only have 2 stages, but if this is a larger scale plant with with higher recovery, we may be able to imagine this kind of configuration, which is so-called the Christmas tree configuration, because it looks like a Christmas tree. So, so in second pass reverse osmosis, we normally choose this kind of configuration, and I'm not so sure if you noticed that or not, but in the Gizang plant, they also had similar configuration for the second pass reverse osmosis. Okay, that's the result that I want to explain here with some time. So since we have 2 reverse osmosis systems, what we were interested in was the effect of recovery on the whole plant performance. So in the first graph, the recovery for the first stage and the second stage was shown in the graph with the over recovery. So the meaning is, if you change the recovery for the first pass and second pass, in this, the total recovery will be changed. It looks very complicated, but if I show you, if I tell you some simple example, you will immediately understand. So let's see that we have the condition that this first pass recovery is 50% and the second pass recovery is 60%. If we reduce the recovery to 40% instead of 50%, the total recovery is reduced from 30% to 23%. So that's the effect of first pass recovery. Again, if you have this this condition, 50% recovery for the first pass and 60% recovery for the second pass, and if you increase the recovery for the second pass, in such cases, the point will move to this direction. So in 70% recovery for the second pass, the overall recovery will increase from 30% to 35%. In fact, this is the same. If you follow this line, you can have the same recovery. So for example, if you have the 50% recovery for the first pass and 60% recovery for the second pass, and if you follow that, and if you arrive that, 30% overall recovery is maintained, even if you have the first pass recovery of 38% and second pass recovery of 8%. So again, in this case, although it's very obvious, but total overall recovery can be changed by changing the recovery for the first pass and the second pass. So in this kind of 2-pass systems, you may imagine that it's quite difficult to operate and operate the system. And in this case, depending on the recovery, the number of membrane elements required to produce 1,000 cubic meters per day of this fresh water will change, because to adjust the recovery, we adjust the flux through the membranes, so that lower pressure means that we need lower flux means that we need to have more membrane elements. So the membrane elements, number of membrane elements required for this system will increase. So obviously, you see, in this case, if the first pass recovery is 56%, and if you reduce the recovery to 40%, the number of elements required to have 1,000 cubic meters per day of this water production changes from 140 and 180. So that's another obvious result, because in this case, we changed the flux to maintain the recovery, and as a result of that, we have this different number of these elements. And the meaning of this total number of elements in this case is the capital cost, because if you have to use more membranes, it means that the membrane vessels, pumps, and other parts will increase. Their size will increase. So we have to spend more money to construct this plant, even if the total water production is the same. So in summary, if you have smallest number of the membrane elements required to produce a certain flow rate of the permeate, it means that this has the lowest construction cost. And by changing the recovery for the first pass, second pass, the concentration in the permeate changes. In this simulation, we have a very optimistic scenario that, and since we have two-pass systems, the salt concentration in the final water is very low. So the concentration ranges from 10 million per liter to less than 3 million per liter. But it's not really surprising, because since we use the second pass reverse osmosis, almost all the salt is removed by the second membranes. But anyway, in this case, depending on the recovery, the water quality changes. In this case, by reducing the recovery, the water quality is becoming worse. In other words, the water TDS, the sodium chloride concentration in the product water increase by reducing the recovery, and it decreases with increasing the recovery. So it's very obvious that we can adjust the sodium chloride concentration. However, in this case, another issue was the boron concentration, and it's quite different because the boron concentration did not change by changing the recovery of the second pass membranes. In fact, boron was difficult to be removed by a second pass membrane, reverse osmosis membrane, and so since their rejection is 4, they show different behaviors with the changes of the recovery. So boron was hard to be removed through second pass recovery, second pass reverse osmosis, without adjusting the pH. In fact, if we wanted to remove boron in the system, we needed to adjust the pH, because boron rejection by the reverse osmosis membrane is sensitive to the pH. So at higher pH, such as pH of 10 or pH of 11, in this case, boron rejection is improved significantly. So we have to utilize that kind of characteristics. Otherwise, in the neutral pH, it was found by the calculation that this boron cannot be rejected. And the recovery also affect the energy consumption in the intake, energy consumption for the pre-treatment, and energy consumption in the reverse osmosis. So let's find out how it is effective. So in the first case, if we have lower recovery, it means that we need to have more seawater to be supplied to the membrane system. So of course, if we decrease the recovery, the energy consumption by the intake increases. In fact, it increases more than 2 times. At the same time, the energy consumption for the microfiltration and ultrafiltration pre-treatment is also same, because if we have a lower recovery, in this case, we have to treat more water by these membranes. So again, we have a clear increase in the energy consumption by this pretreatment with lowering the recovery in both first pass and second pass. How about this first pass reverse osmosis? It's quite interesting to see how it changes with the recovery. In fact, the recovery, if you adjust the first pass recovery, in this case, around this 35% of recovery, it shows the minimum value. And if you have lower value, in this case, it's not quite sure, but if you closely look at that, the energy consumption slightly increases here. And so again, in this case, if you increase the first pass recovery, the energy consumption increase, and if you decrease the first pass recovery, it generally decreases, but there is a optimum point that we can achieve the minimum energy consumption. And in the second pass, if you increase the second pass recovery, we can reduce the energy consumption. And the reason is, if we increase the second pass recovery, we can get more water. So although we use same energy in the first pass, the specific energy consumption is changed by the amount of this water produced by the second pass reverse osmosis. So the idea is so in fact, the second pass recovery does not affect the energy consumption in the first pass reverse osmosis. However, by changing the second pass recovery, the volume of water or flow rate of water at the end of the plant will change. So if we have a higher recovery for the second pass, in this case, V2 will be larger than V1. So that's SCC, that's SCC. So the SCC at higher recovery will be lower than this SCC for the lower recovery. And the final result here is the energy consumption for the second pass reverse osmosis. And in this case, the first pass recovery does not significantly affect the energy consumption in the first pass recovery. So in this case, recovery, the first pass recovery is the dominant factor affecting the energy consumption in the second pass recovery. And in fact, this recovery for the second pass is not really important in this case. So we have to combine everything to calculate this energy consumption. So we have to add this energy consumption by the intake, pretreatment, first pass, and second pass. And the final result looks like that. So in this case, what you can see is when you have the recovery ranging from 0.2 to 0.5, we have this lower energy consumption. So the optimum recovery for the first pass reverse osmosis is between 0.4 and 0.45. In fact, it's 0.4 and 0.45. So around this region, we can have the condition for having lower energy consumption. And in the case where we just do this second pass recovery, again, if we increase the energy, the second pass recovery, we can a little bit decrease the energy consumption. So we can even reduce 25% of this energy consumption by increasing this second pass recovery. So in summary, in this kind of system, the optimum recovery for the first reverse osmosis is between 0.4 and 0.45. But in the second test, the highest recovery is recommended to reduce the energy consumption. And since this energy consumption is the dominant factor affecting this operation cost, so water production cost is always also has a similar patterns with this energy consumption. Temperature can change a little bit. So in this case, by increasing the, we have two cases for the product water sodium chloride concentration, normal concentration and very low concentration. And if you compare the left figure and right figure, the salt concentration at low temperature is much lower. Again, as I already explained, salt concentration or salt rejection is improved by reducing the feed temperatures. This is because the membrane becomes tighter with the temperature. So in terms of the salt rejection, lower temperature is better. If we compare the situation in Korea and in Gulf region, in Korea we have relatively low seawater temperatures and low seawater TDS, and in Gulf region they have higher temperatures and high TDS concentration. So in this case, in terms of this permeability quality, in Korea